Guest today is Dr. Peter Levermore, co-founder and CEO of Excyton in the UK. Peter got his doctorate from the Imperial College London and has built an impressive international career with Sumitomo Chemicals, Universal Displays Corporation, CSEM, and Merck. And today, Peter will share with us his expertise on the latest developments in the field with a talk titled OLED Displays Design. Right? And after Peter's presentation, we will have today a special guest. This is going to be Fluxim CEO, Professor Bert Ruhstaller, and Bert will present our brand new software to calculate and optimize the power consumption in OLED displays. So, Peter, the floor is yours. Thanks for joining us, and we are looking forward for your talk.
Okay, thank you very much. Okay, let me share my screen.
Perfect.
Right, hopefully that's showing up okay.
Yep.
Excellent. Okay, so let's get started. Yeah, okay, so I'm the CEO of a startup company called Excyton. Excyton is based in the UK. We're actually up in the city of Durham, which is in the northeast of England, quite near to Newcastle. Beautiful city, as you can see there with the cathedral and castle there in the background. And we're at a small technology park just outside of Durham. The company was founded in 2019, and our focus is very much on OLED display designs, and in particular looking at the individual pixels, be it red, green, or blue, and how the structures of these pixels and the layouts of these pixels can be optimized to really increase the performance of the display. In terms of just quickly, I'll introduce the team and then I'll kind of go into some of the display designs. So the background is myself. I'm the co-founder of the company. My other co-founder is Professor Daniele Braga. He was one of the inventors of polymer electroluminescence and a founder of CDT many years ago. And we also have Professor Chu and Professor Sui from Cambridge and Oxford University, respectively. And so, as I said, together we are the team sort of behind Excyton. And as we all know, in terms of when it comes down to displays, there's always, there's obviously generally many parameters that we're looking to optimize, but we could kind of break it down to efficiency. You always want more efficiency on the display. That could be because with greater efficiency, you have a longer battery life, or you can have a smaller battery, or it could just be with greater efficiency, you can put that back into the display, make it brighter, make the refresh rate faster, make the color gamut wider. But you always want efficiency. Color is an ongoing challenge. Most state-of-the-art OLED displays have what's called a DCI-P3 color gamut. So that's kind of 52% of the visible colors is what they render. It's been a long-standing challenge within the OLED industry to take that color gamut out to Rec 2020, trying and capture 76% of the visible colors. And finally, it's an ongoing problem still with displays is lifetime, and particularly blue. Commercial OLED displays today, none of them use a phosphorescent blue, and they use phosphorescent red and green. But for lifetime reasons, commercial displays today still use a fluorescent blue that has 2 to 3 times lower efficiency in terms of external quantum efficiency than the red or the green. So these are generally the sort of the challenges that OLED face. But what I'm going to do now is just take a little kind of step back and talk about what do we mean by an OLED display design, because often when you say, hey, it's an OLED screen, everyone thinks, oh, it's an OLED. But in fact, at the moment, there are around, if we discount passive matrix displays and just look at the active matrix displays, there are actually 5 different OLED designs that you could have in a commercial product. So the first one is what we're familiar with is RGB. So for example, if you have your smartphone such as this will be an RGB display and it will be top emission. So that could be the iPhone or the Samsung Galaxy. But perhaps if you bought the latest iPad Pro, or maybe you have an OLED screen in your car, an automotive display, then what you're going to get is the tandem structure. This has actually become very popular since Apple used it in the iPad Pro about a year ago. And here we stack red, red, green, green, blue, blue on top of each other in series. This is going to obviously make the display a lot brighter and have a longer lifetime because we're doubling the emission from kind of each unit. But then maybe we've got an OLED television. Now I'm actually simplifying it here, but the OLED television is what we call RGBW. So there are red, green, and blue pixels, but there's also a white pixel in there. These tend to be bottom emission because they're lower resolution. Here I'm showing a simplified kind of version of the stack where I'm showing red, green, and blue stacked on top of each other to make white. And then we have red, green, and blue color filters below, and then the white light passes. Actually, the OLED stack is a little bit more complex than just red, green, and blue, as we'll go into in the later slides. But you see here we have a completely different structure for OLED television compared to, for example, a tablet or a smartphone. But then maybe you didn't buy an OLED television from LG, maybe you bought one from Samsung. Well, if you bought a Samsung OLED television, then you have a different design altogether again. Here you have fluorescent blues stacked on top of each other. You have top emission instead of bottom emission. And what you do here to generate the red, green, and blue is you actually use quantum dots and down conversion rather than color filters. So again, the Samsung OLED television is a completely different pixel design. And then, we can go one step further. What if you have the Vision Pro, the little headset from Apple, very, very high resolution? Well, that would be something different again. That would basically be a white OLED with color filters on top of it. So what I kind of wanted to do with this slide is really just kind of highlight that when we say it's an OLED display, it really does depend on the product and even the manufacturer in terms of exactly how those pixels are laid out, whether it's top emission, whether it's bottom emission, whether there are color filters, whether there are quantum dots. It really does change kind of with every product. I'll just spend a few moments just because I think it's kind of interesting just as a little overview here to go into some of them kind of like specifically. So this here would be RGB. This is by far the most common. I'll bring up the laser pointer actually here. Yeah, by far the most common. So what you have is red, green, and blue pixels. Light emits from the top, so it's actually emitting away from the substrate. And if you actually look, the pixel layout is usually what you call a diamond pixel. So typically the pixels are laid out like this. The blue pixel is the biggest because this is kind of where we have our biggest kind of lifetime and brightness concerns. The green pixel tends to be very, very small. This layout has really been used since the Samsung Galaxy S 2010. We've had basically RGB kind of top emission OLED in the Samsung Galaxy since 2010. Back then, as you can see, our smartphones were only 4-inch and 233 ppi. Today's kind of versions, we've kind of gone up to a 6.8-inch display and significantly higher resolution. But actually, they still remain RGB top emission, and they kind of always have been. And the same goes for kind of the Apple iPhones and really any other kind of smartphone that costs more than about $100 will be OLED. More recently, we see this tandem structure. So this is what I talked about, like, for example, if you have the iPad Pro, but you can now also have automotive displays with this. If you buy the Dell XPS 13 in 2014, the screen on that is also tandem RGB. You can see from this design here, it remains top emission, and we've simply put a red on top of a red, a green on a green, and a blue on a blue. What's very interesting is that the pixel layout changes. So we tend to have what's called S stripe here, rather than the diamond pixel. I'm not sure exactly why this is, but we are dealing with a kind of a slightly lower resolution because obviously the viewing distance is slightly greater for tandem. If we go on to the RGBW, here you can kind of see here the very first LG kind of OLED television, 55-inch. It cost $12,000 back then. You can now pick this up for $1,000, $1,200, something like that. But you can see the latest OLED television up at 97-inch. You can actually buy it now. That's $25,000 if you want kind of the highest end kind of OLED TV that's out there. When you look at this here, as you can see, you basically generate white light by putting yellows, reds, light greens, blues, more yellows on top of each other. Then you have the red, green, blue color filters. The white light just passes. Resolution's much lower for a television, only 80 ppi. And you can see here, they just use stripes. So we don't have S-stripe or diamond pixel in the OLED television. You actually just use a simple kind of stripe approach here. QD-OLED, again, this is what I showed you here. We stack blue on top of each other. This is the Samsung television. You have down conversion in red, green, and the blue light passes. It's top emission. Again, pixel layout is completely different from all of the other displays. You can see this kind of changes here. The television is kind of, it's not really shipping in great units. Really, the LG television maintains the dominant position. What is interesting is that the gaming monitor that Samsung have launched with QD OLED is tremendously popular. Yeah, this is really selling very, very well indeed, the QD OLED monitor for gaming. So that may be, you know, the future of QD OLED, may be more like the kind of the monitor displays where it's doing very, very well. And then finally, what I said, the Vision Pro here. Here we have basically white emission, color filters, little kind of domes here, incredibly high resolution, 3,386 ppi, so 23 million pixels in a tiny kind of little display here. And again, you have a kind of a different pixel layout. So again, I just wanted to use those slides just to kind of highlight, you know, when we talk about OLED displays, everything's different. It really does depend on the display that you're choosing. And so here at Excyton, what we kind of thought about was, well, like, you know, let's kind of do a thought experiment here, and let's try and think what is the most efficient design that we can think of for a display. And what we came up with was what we call a TurboLED. So if we take as a starting point the iPad Pro display, so this is the tandem RGB structure, which was launched last March, April. And what we've done is we've adapted that in two ways. So the first thing that we've done is we've replaced the deeper colors on the top here with lighter colors. So we have a deep red and a light red, deep green and light green, deep blue and light blue. And then the second change that we've made is we've made electrical contact to the middle electrodes. So the difference here is that whereas in the iPad, we're lighting these emissive units up in series together, in a TurboLED display, we can select. So we can choose to either turn on the light or the red or both at the same time. And so we can kind of tune that depending on the image content. And so this design here is fundamentally a TurboLED display. So as I said, it's just a couple of steps kind of forward from what's kind of in the iPad at the moment. And why would you do that? Well, the reason you do it is because, as I'll kind of demonstrate to you, you can actually reduce the display power consumption in half. You can make the display more colorful, and it also gives you a path to longer lifetime. And I'll just see if there's a little video here. This shows one of the displays in action. So you can see a light green pixel and a deep green pixel on top of it. So I'm just alternating which one I turn on here. The light green and the deep green, they're just kind of on top of each other. These are sort of 1 centimeter by 1 centimeter demos. So the question is, why would we do all this? Why would we stack light on top of deep? Why would we address them independently? So if we kind of just look at the physics of it here, what you see here is the sensitivity of the human eye. So it peaks at around 557 nanometers. Our eyes are extremely sensitive to yellow greens. Obviously, our eyes cannot see infrared or ultraviolet. And you have kind of like almost like this bell type curve here where our eye sensitivity really drops off for these deeper blues and deeper reds. And what you see here, this would be a standard deep red in a display. You can see that our eye is around 40% sensitive to a deep red. Whereas a light red our eyes are much more sensitive, twice as sensitive. So what it means is that for a light red, for the same number of photons, our eye will perceive that display to be twice as bright, just simply because, our eye is a better detector of lighter colors. You can do the same kind of thing for the deeper green and the lighter green, and the deeper blue and the lighter blue. The big difference as well with light blue and this kind of increase in sensitivity here is that because this light blue is peaking at around 480 nanometers rather than sort of 465, it becomes very possible to use a phosphorescent light blue here. The wavelength of 480 nanometers really is more attainable to have kind of like a stable excited state, so that a phosphorescent blue could be used in the display. So that's the first element of it, just simply that because of our eyes, light colors are more efficient. The second kind of element behind it is to think about, the displays and what kind of colors do you normally see on a display. And what I normally do is I invite people just to look around them in the room they're in now, or look at the screen in front of them, and ask the question, how many deep red, green, and blue colors are actually on the screen? And the answer is always usually not many. In fact, a very small proportion of what's on the screen is usually a deep red, green, or blue. And here we look at kind of 1400 test images from all sorts of kind of different content. Could be web browsing, movies, cartoons, word processing, gaming. And what you see is by far the most common color on a display is white, here at the D65 white point. By far the most common color. You then get a lot of colors around the white point here. And then as you go to, like, for example, deeper red, deeper green, and deeper blue, you see very few colors indeed. And then, as I said, there's always this little thing here right at the very end, the deepest red, the deepest green, and the deepest blue. There's a little spike, and that's simply to do with web design, whereby somebody designing a website will say, okay, give me the deepest red for this icon. They never choose the second or third deepest red. But as you see, this area here, very few kind of deep colors. So when we combine those two things together, the fact that most images on the display are light in color and the light colors are more efficient, you can kind of see why the TurboLED design has its advantages. I also highlight that point here. Here you see a very colorful image, tulip fields in Japan. But actually, when you break it down, only 11% of that image requires deep red. Only 11% requires deep green. You can see it's where the black pixels are here, is where you actually need to turn on the deeper colors for red and green. And only 1% of this image requires a deep blue. It's this tiny little bit of the field just here. So again, you kind of highlight that sort of point. What we can then do basically is working with Fluxim, and Beat will show kind of the display power calculation tool. We've been using kind of like a beta sort of version of this to demonstrate that TurboLED really does produce significant power savings. And so I'm showing you here what would be the typical color gamut we would use for the deep red, green, and blue. That's DCI-P3, and then an optimized lighter color gamut, which will encapsulate most of the images on the screen. We then put in these input parameters. So again, for deep red, green, and blue, we're using DCI-P3. We're assuming a 25 nanometer sort of a frequency width half maximum. This data in terms of from Candela per amp is basically taken from Summer Sprout Technology, who provide commercial materials for red, green, and blue. And then what we've done for the lighter colors is assume the same EQE, and we're using a light blue based on UDC's latest data up at 60 candela per amp, because as I said, we're at a more accessible peak wavelength where phosphorescent blue is useful. So we put in the same image. What we can do with the software is we can map out the power consumption for every single pixel. So you can see here for the iPad Pro, we would have 5.92 milliwatts per centimeter squared, very high power consumption in this light blue sky here. Whereas if we use a TurboLED display, we can really reduce the power consumption across all of the pixels, but especially where there are light blues here. And what we see here is 45% less power consumption. In a smartphone, that will be 4 hours extra battery life each day. If we do the same thing for an image where there's a lot more blue on it, what you can again see here is that the TurboLED reduces power consumption actually even more because there's just more blue on the image. So here we have like 47% power savings. So, this is obviously very, very good. The other advantage of this is that typically in a display, there is a trade-off. One of the reasons people don't make these Rec 2020 displays with the wider color gamut is that because if you were using those really deep red, greens, and blues for all of your images, your power consumption would go up probably 30 to 40%. However, in the case of us, we're only using those deeper pixels less than 10% of the time. Therefore, we can actually get to Rec 2020 with a very, very, very small increase only in power consumption. The other element is that because we're using a light blue for, again, 90% of the images, we're no longer dependent on the deep blue lifetime. So we can extend the lifetime of the display. If we kind of then circle back just to all of the other display designs that I showed you, RGB, tandem RGB, RGBW, QD-OLED, and white plus color filter, and then I introduced the TurboLED here. What you can see is we don't use color filters, we don't use down conversion, we don't use deep pixels to make kind of light pixels. And so what you can see here is that the efficiency, if you compare it, for example, to the television of OLED, you're seeing 5 times greater efficiency. But even compared to the tandem structure, it's around 2 times greater efficiency. And I can kind of map this out here on a sort of a chart that shows kind of efficiency against color. So really, we did put forward TurboLED as like, really this is the most efficient way that you can design a display. We have then made prototypes. So working with summer sprout materials, we've made prototype deep and light red, green, and blue. You can see here from the color gamuts, what we have succeeded in making. And again, you can kind of see the test pixels here, the lighter and the deeper color gamuts that we've achieved. So we have actually made these prototypes. Just to kind of finish off, I will say, of course, this technology is patent protected. These patents have been granted already. So we have a very good position on this technology. And because of that, we did win the Innovation Award at SID, basically for this design. So each year at SID, they give an award for what they think are the most sort of innovative designs in displays. We also received a substantial grant from Innovate UK and InnoSwiss to continue working with Fluxim and Durham University to demonstrate a prototype display, which we should have around 2 or 3 months from now. And also we received some funding from Oxford University to work more with our partners in Europe on this. So I think I'll probably kind of actually finish off there. I'll kind of skip over this last part here, I think. And just say kind of thank you very much to our partners, particularly at Fluxim, Durham University, at Summer Sprout, and at Kaust, who are our investor. Okay, thank you very much.
Thanks a lot for this very informative presentation, Pete. Myself, I have a couple of questions. The first one is, actually, you have been showing the TurboLED as an amazing characteristics in terms of power consumption and brightness, but which are the challenges to fabricate such a display?
Yeah, so I mean, there are several obviously challenges around it in terms of it being a different structure, but this slide here shows it. So as I said, there are 2 things that are different between this and, let's say, the iPad. So the iPad is already in mass production. So 2 differences. One is that I changed the deep colors for the lighter colors. That's actually very easy. Lighter colors are much more stable than the deeper colors, so there's no real challenge whatsoever, but you just have to change the color. The technical challenge is basically how do you make contact to the middle electrode? That is that's it basically. Everything else around this is very straightforward and achievable with some work. Yeah, you have to do some kind of recalibrations for the second gamut. But yeah, the technical challenge in the main is making contact to the middle electrode.
Is there a technology that can do it, or do you need to invent it from scratch?
No, I mean, you can do it. It's just that obviously you you need to add essentially an extra via by each pixel. So of course, typically in a a kind of an active matrix display, you'd obviously just have your anode and your cathode there. What we actually need is you effectively need to make a via and make a contact to that middle electrode. So really that's the most challenging element of it. You know, at the moment, as part of the project, the Disco project with Durham and Fluxim, you know, we are making a little prototype display. It'll only be like 200 by 200, but you know, where we'll demonstrate how it's possible to do that, you know, on a kind of a small scale display.
Okay. We have here a couple of questions. You stacked two different colors on top of each other via semi-transparent electrodes. So my question is, how efficient and stable is the middle transparent electrode?
Yeah, I mean, so the thing is with the middle electrode is we call it an electrode because we're making contact to it, you know, but in terms of its characteristics, it's really not that different from just a standard charge generation layer. And as I said, these charge generation layers are already used in countless commercial devices, not just the iPad, but for example, as I showed with the RGBW OLED television from LG or the Samsung television, you actually have three of these things on top of each other. So you have two middle electrodes there already. And in fact, at CES, both LGD and Samsung have said that the next generation, they will even go to 4-stack. So actually the next generation of OLED televisions will have 4 stacks. And so therefore they will have 3 of these middle electrodes in there. So really middle electrode kind of transparency isn't a particular kind of concern or challenge. As I said, it's a very standard technology to see this. You see it in all OLED televisions already.
Right. There's a follow-up question here. Whether you can control both the shades of the same color at the same time.
Yeah, you can. So I mean, you obviously there's some kind of little smart tricks around how you make electrical contact and how the circuit works. But yes, you can certainly turn the lighter and deeper on at the same time. And control them independently, you know, like that's yeah.
Right. Okay, we have a last one here. How does the power consumption of TurboLED and tandem LED compare for images with mainly white light?
Yes, I mean, actually, kind of when there's white light, you really see very, very good power savings from it. So I mean, I'll see if there's one of these display images here. This would be a kind of an example here, I suppose, you know, of what we're kind of looking at. Because in white light, I mean, actually, I'm trying to think where the best way to show this is in terms of what I have here. Yeah, here. So, you know, if we think of white light as being here, in a normal display, you would actually have to turn on the deep red, the deep blue, and the deep green to make this color. White is a very good color because I can actually use the most efficient light red, light green, and light blue for white. So actually we get, yeah, kind of almost 50% power savings in the white, because it falls where we can use all 3 of our lighter colors there. So inside this triangle is where the power savings are at their greatest.
Right. Another one, controlling the different colors is a much greater effort for the manufacturer. Are manufacturers willing to do this?
Yeah, no, I mean, it's a very good good point. As I said, the challenge of TurboLED is more in the back plane than the front plane. The front plane is very straightforward to make it. Really, it's no more difficult than making the iPad. You know, this is actually where we've been having a lot of fun the last kind of 6 months talking to display manufacturers about all of the different possibilities for how you can drive these kind of these pixels, and we're actually making some very good progress. So we do now have some joint collaborations with display manufacturers, looking at the different ways of doing the TFT design, and the reason they're interested is because the benefits are so great. I mean, 50% is just such a huge amount that we are now starting to have like R&D collaborations with display manufacturers working on the different backplane designs.
Amazing. Right, this was great, and please stay with us. Right now, we are going to start showing you the software tool that we developed to calculate power depending on the picture or the picture that the display is showing, as Peter was showing before. Please, Bert, can you join the webinar? Yep, we see your presentation. We still don't see you. And you're muted.
Okay,
great.
Here we go. Thanks, Daniele, for introducing. Yeah, I would like to take this opportunity to add a few slides on our development of this display power consumption calculation tool that Peter mentioned. And so I'll start out with this overview slide where you see kind of a workflow. So you would want to input or have ready the JV and L luminance characteristics of your subpixels that you want to build into the display. And these subpixels have a certain color gamut, as is indicated in this graph. Then you choose an image or multiple image that the software will process and then calculate the power consumption that is mapped out pixel by pixel. So you really get a power density here, information of that chosen image. And then you can start playing around with different designs of the displays. This particular image indicates the TurboLED concept that Peter focused on. And on the lower right, we see one of the main benefits, as is obvious, by saving power consumption, you can actually extend the battery life of a given mobile device. Or an alternative could also be to invest the energy saved into brighter display. On the left here, we see different schemes of subpixels, 3 subpixels side by side, there's 3 subpixels on top of each other, and also these 6 subpixels at RGB, each one having double of each one, or the approach of light and deep colors combined. Of course, the established RGBW, the white, the 4th pixel being a white, that concept is also capable to be calculated with this software. So I would like to give you a brief preview. And the screenshot here of the software actually shows not only a sneak preview of the software, but also maybe of your upcoming summer vacation. So this image of a beach with palms and blue sky is actually, as Peter just indicated, it's an image example which has a lot of light colors. So the statistics of the pixels of this image is actually only occupying a part of the color gamut that is available here. So now, how does the user interface look like? So we have a workspace on the left where you can prepare several different display concepts. And for each of them, you will choose the subpixels, whether in this case there are 6 subpixels, but as I said, it could also be 4 subpixels, one of them being white. Then you also define the JVL data. You import that and you define the colors of each subpixel. And then you choose your image to be analyzed. And then after you finish the calculation, you get a statistics of the usage of all the subpixels, how much of these pixels have actually used and have what's the fraction of power that they have consumed that they will consume to actually display that image. And then, of course, you can repeat this by doing using a different display concept. And this is an example of the TurboLED concept with Peter's company Excyton that is talked about. So in this example, you see the traditional RGB display would show you rather high levels of power inside this image. Then if we switch to this TurboLED concept, you see that the power level is reducing significantly. In this particular example, it's 36% power consumption saving. Now, just to give you an outlook, my final slide. So why do we do this? Well, we have started out with a Setfos simulation software for OLED stack design more than 20 years ago. It's a 1D software where you calculate charge transport and excitonics inside the OLED stack, and then light out coupling with or without light scattering enhancements. Then 10 years ago, we actually launched the software LAOS, which is a large area design tool where you can define the subpixels side by side and do calculations of electrical properties, thermal properties, and as well as optical properties. So you could study things like electrical and optical crosstalk, and do that for whatever subpixel layout you choose. And now for us, this new display consumption tool is actually a logical step if we want to go to the system level, to the display level, rather than just individual pixel or pixel arrays, but actually looking at the behavior of the entire display, where the user chooses the resolution of the display that he wants to analyze and subpixel choices. So this is the software we're going to introduce later this year, and this is just preview, and we're always happy to get in touch with interested possible users of this tool. So please contact us if you have inquiries about this upcoming software tool that we are commercializing this year. Thank you for your attention.
Great. Yeah, thanks a lot. I was going to say the same thing. The tool is going to be ready soon. So if you have any questions, Pete, if you want to test it, just we are ready to let you test it. We have another question here for Bear this time, and then a couple of questions for Peter. Bear, they are asking you if this software can calculate LEDs with ion migration.
Actually, the idea is we provide a set of tools. So if you care about charge transport, whether it's free carriers, electronic charges, or ionic charges, then you should be using the Setfos tool, the drift diffusion module of it, and it allows you to calculate current voltage curves, which you then store and then load them into the display power consumption tool. So you have to do it two-step. First, calculate the JV behavior in the Setfos tool, and then import that behavior, that curve, into this new display power consumption tool. So they are complementing each other.
Yep. And Peter, they are asking you if this TurboLED new concept utilize a specific material such as perovskite, organic, inorganic, or is primarily a structural enhancement to improve performances?
Yeah, so it's primarily a structure. As I said, the key element of it, so it could work with perovskites or quantum dots or any kind of material. The key point, though, is that particularly because the light blue, being at this kind of 480 nanometers, it gives you the opportunity to look at phosphorescent light blue or TADF light blue, which, down at the deep blue level, the stability really wouldn't be good enough for a commercial product. So it does open up a couple of interesting, more efficient material classes there. I also saw there's a question of do I actually have a device? So I thought, I actually forgot to do that. So this is kind of like a little demo here. Let's see if I can get it to work. So that would be, for example, the deep green here. And then if I flick it here, you can see kind of the light green So the DM is obviously going to saturate. The light green is actually more like a yellow, as you see, but you can kind of get the concept there of how that's sort of working with the light greens and the deep greens, and you can just as you like, you can kind of alternate between them. As I said, we did also have some fun kind of just making a really tiny version of it with like a little battery here. So you can kind of see here the deep red, again, it's going to saturate, which will flip to the light red here. But you can kind of see this very sort of nice like little demo here in terms of how it works for the red and the light as well. And obviously in each case, when I go to the lighter color, it's clearly going to get brighter. And that's, as we said, it's because the eye is far more sensitive. It's still running off the same voltage. These are running off like a 3-volt battery.
Right. Thanks a lot. And Beat, if you were an external speaker, I will have another question myself. How much will the software cost? But I know that we don't have the price yet. So everyone which is interested in trying out at the moment is
should contact the sales team
and should just contact us. All right. So thanks a lot, everyone. I think we are at the end of our webinar today. The next webinar will be the 15th of April at 10 a.m. There's going to be Dr. Anna Kanerce from Germany, and we are going to go back to solar cells. So this time, another topic, new challenges in fabricating tandem PVs. Thanks a lot for your time. Thanks, Beat. Thanks, Pete, once more. And I will see you the next time.
All right, thank you very much.
Bye-bye.
Thank you. Bye-bye.